Hi, this is Math 2520, and this video is over section 10.7. We're going to get into two other tests when it comes to sequences. The first one's the ratio test, and then we'll get into the root test. Each has a certain situation where when you see this kind of form, you should think of this test. So first recall that n factorial is n times n minus 1 times n minus 2 all the way down to 2 times 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, which is 20, 60, 120. Alright, so now we're going to consider this series summation from 1 to infinity of 1 over n factorial. Can we determine whether it converges or diverges? Okay, so first we're going to look at the ratio test. Given series summation a sub n, let n limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n equal L. If L is between 0 and 1, then the summation for a sub n is absolutely convergent. If L is greater than 1, then the summation is divergent. And if L is equal 1, then the ratio test is inconclusive. We don't know if the summation a sub n diverges or converges. So there's a possibility that this test doesn't end up helping. Okay, so now let's go back up to our example 1 over n factorial and use this ratio test to see if it converges or diverges. And one of the reasons this helps with things with factorials is you can get a lot of those terms to cancel out using the ratio test. So we're going to look at the limit as n goes to infinity of 1 over n plus 1 factorial over 1 over n factorial, which is the limit as n goes to infinity of n factorial over n plus 1 factorial, which is the limit as n goes to infinity, and this is why this ratio test works with things with factorial, is the top is going to be n times n minus 1 times n minus 2 all the way down to 2 times 1, and the bottom is going to be n plus 1 times n minus 1 times n minus 2 all the way down to 2 times 1. So we see that a lot of things cancel all the way down. So what we end up with now is the limit as n goes to infinity of 1 over n plus 1. And if n is going to infinity, then that bottom gets really, really high, and so the whole fraction goes to 0. Okay, and so now if it's 0, between 0 and 1 including 0, then you have absolutely convergent. So this series is absolutely convergent. Okay, let's do the next one. N factorial over 100 factorial. Okay, so we will look at the limit as n goes to infinity of n plus 1 factorial over 100 factorial over n factorial over 100 factorial. And so this becomes the limit as n goes to infinity. Flip this fraction, n plus 1 factorial over n factorial, and then the hundredths cancel out. And so we have the limit as n goes to infinity of n plus 1 times n minus 1 dot dot dot, and the bottom will be n times n minus 1 dot dot dot. And so all the terms but n minus 1 cancel out. So we have the limit as n goes to infinity of n plus 1, and that's going to go to infinity. And so we go back up here. If n is greater, L is greater than 1, then it is divergent. Infinity is going to be greater than 1. So this series is divergent. Oh. Okay. So I gotta go back to this. At least it let me finish the problem. So I didn't have a chance to write it, but this series is divergent. Alright, so we'll do another example. This one's going to be 1 over n. Now notice there's no factorial sign, but this still can be something we try. Limit as n goes to infinity of 1 over n plus 1 over 1 over n. This becomes limit as n goes to infinity of n over n plus 1, which we can write this as the limit as n goes to infinity of 1 over 1 plus 1 over n. Just divide top and bottom by n. And as n goes to infinity, this becomes 1. Okay, so in this case, the test is inconclusive. Couple more problems. Here, 4 to the n, n plus 2 times 2n factorial, and then 2n plus 2 factorial. Okay, now this whole thing is on the factorial. Okay. So we'll do. Oh, I'm sorry. Let me double check this. No, it's not. Only that 2n is. Yeah. So we'll have 4 to the n plus 1. Let me write up my limit. Limit as n goes to infinity, 4 to the n plus 1, n plus 1 plus 2, and 2 times n plus 1, and that'll be factorial. And this will be over 2n plus 1 plus 2 factorial. Alright, and then the whole thing will be over 4 to the n plus 2, 2n factorial over 2n plus 2 factorial. Alright, so let's write this out with the factorials. So limit as n goes to infinity, 4 to the n times 4, I'm going to write it like that, n plus 3. And then we'll have 2n plus 2 factorial. And then the bottom also has this will come up. I'll bring this up to here. So this will be another 2n plus 2 factorial. And this bottom would be 2n plus 4 factorial. Four to the n. I'm bringing this up. So I'm flipping that fraction. 4 to the n plus 2, 2n factorial. Okay. So now we gotta look at what will cancel. Okay, first 4n and this 4n cancel. And so we have a 4 on the outside. And we will have n plus 3. Don't. N plus 3. And then the 2n factorial here. So we cover that, 2n factorial, 2n plus 2 factorial. You know, as we go down, we'll have 2n plus 1, 2n, and then 2n minus 1, and so on. As well as in the bottom would be the 2n and the 2n minus 1. So this will cancel with the top, except for 2n plus 2 and 2n plus 1. Let me double check where I'm at. Okay, so then on the bottom we have n plus 2. Okay, now for the bottom and for the top, notice the one thing I haven't covered is this term and this term. Okay, same idea. The 2n plus 4 is one term that will still be there. And you'll have 2n plus 3, but then you'll have 2n plus 2 factorial that cancels with this. Okay, so that's how that cancels out. So this is everything you have left after the cancellation. Right. So now what we can do is we can multiply all this out. Right. I'm not going to go through all the multiplying. I'm just going to write it out. You'll end up with 16n cubed plus 72n squared plus 80n plus 24 over 4n cubed plus 22n squared plus 40n plus 24. Okay, and we'll end up with the limit as n goes to infinity. Right, so divide across by n cubed. So we'll end up with the limit as n goes to infinity, 16 plus 72 over n plus 80 over n squared plus 24 over n cubed over 4 plus 22 over n plus 40 over n squared plus 24 over n cubed. All these terms go to 0, and so this one ends up being 16 over 4, which is equal to 4. And if we go back, 4 is greater than 1, so the series diverges. All right. And the last one example we're going to do for the ratio test, 4n over n factorial squared, or the limit as n goes to infinity, 4n plus 1 over n plus 1 factorial, that whole thing being squared, which, you know, I'm going to write it this way, since it's being squared, get rid of these parentheses, it's just n plus 1 factorial times n plus 1 factorial. Okay, maybe easier to write it that way. Over 4 to the n, and then n factorial times n factorial. Okay, so for the limit as n goes to infinity, 4 to the n times 4 times n factorial times n factorial over 4 to the n times n plus 1 factorial times n plus 1 factorial. Oops. Okay, so this 4 to the n's cancel, the n factorials cancel with the rest of them, so you have just 2 n plus 1s on the bottom. So we'll have the limit as n goes to infinity, 4 over n plus 1 over n plus 1. Both of those, as is being raised to infinity, are going to go to infinity. So this whole thing goes to 0. And so since L is less than 1, and actually since it's equal to 0, you have absolute convergence. So that's the ratio test. The root test, we want to do a couple of examples. The root test is when you have a sequence being raised, and the whole thing being raised to a power, but the power itself is the end. And so that way we can take the nth root of the sequence and find if it converges or diverges. Right, so given a series a sub n, we'll have the limit as n goes to infinity of the nth root of the absolute value of a sub n, and that's going to equal k. And if k is between 0 and 1, then we have absolute convergence. If a is greater than 1, then it's divergent. And if a is equal to 1, then the root test is inconclusive. This is one of the reasons these two are taught together. It's almost the same kind of rule in a sense. Alright, so 5n squared minus 3 over 8n squared plus 7. We'll do the limit as n goes to infinity, the nth root of 5n squared minus 3 over 8n squared plus 7 to the nth power. And so we get the limit as n goes to infinity of 5n squared minus 3 over 8n squared plus 7. This is always going to happen because you can only use this with when everything's being raised to the nth power. Right. And so we can divide all terms by n squared. So limit as n goes to infinity of 5 over 8 minus 3 over n squared, 7 over n squared. The 3 over n squared and 7 over n squared, they go to 0. So this is going to be equal to the absolute value of 5/8, which is equal to 5/8, which is less than 1. So the series is absolutely convergent. Last example. Now, we can do certain ones, but notice there has to be a power to the end in some way. So here we're going to take the limit as n goes to infinity of the nth root of 3n over n squared. And so we can break this up. Limit as n goes to infinity. Keep forgetting my absolute signs. Of 3 to the n to the 1/nth power. That's not 3n, that's 3 to the n. Oops, almost did to the 1n. Okay. Over n squared. Gonna be a limit as n goes to infinity. 3 to the n to 1/nth over n squared to the 1/nth. Okay. 3 to the n to the 1/nth is just going to be 3. And n squared is going to be n to the 2 over n. Okay. So now, what happens when n goes to infinity? Well, 2 over n as n goes to infinity goes to 2 over infinity, so it goes to 0. Right? But we have to be able to figure this out in order to do this one. So it doesn't matter what n goes to. N goes to infinity, yeah, but 2 to the n goes to 0, which means that bottom goes to 1. And then 3, it stays 3. And then 3 is greater than 1, so series diverges. Alright, so that's the ratio and root test. In the next section, we will be going through a lot of different examples going back to the tests we have. So it won't be any new tests, but we just will go through a lot of examples. If you want to try these beforehand, it may be good. Get some practice and then watch the video and just find out maybe where you went wrong or if you got the answer right. Alright, and I'll see you then. Bye.